In 1918, the Pennsylvania Railroad tested a prototype with 140,000 pounds of starting force, more than double what the couplers holding its freight cars together could survive. They called her Big Liz. She never broke down. She never malfunctioned. She simply tore apart every train they coupled behind her. The question was not whether Big Liz was flawed, but whether the entire railroad was ready for her. In 1917, inside the Pennsylvania Railroad's Juniata shops, a new kind of locomotive took shape. Number 3931, soon called Big Liz, was the vision of Chief Electrical Engineer William H. Smedley, a machine built to do what steam engines could not: pull heavy trains over the steep Allegheny grades with a single unit. Smedley's ambition was clear. The Alleghenies had always demanded double or triple steam engines, burning through coal and time. Big Liz promised something different. Vision at her core, 4 Westinghouse induction motors produced a combined 4,600 horsepower, all managed through a rotary converter system. The spec sheet claimed a starting tractive effort of 140,000 pounds of force, a figure unmatched in American freight. The mission was bold: to replace steam on the mountain grades, cut fuel costs, and move more coal and ore to the steel mills that powered Pennsylvania's industry. Power. By February 1918, Big Liz faced her trial, a full-length freight climb from Philadelphia to the summit near Altoona, a route notorious for its 3% grades. The test train, 30 to 35 cars loaded to capacity, weighed in at nearly 1,500 tons. Smedley and his team watched as the locomotive prepared to answer a question that reached beyond one railroad. Could electric power truly conquer the mountains? Trial. As the test began, Big Liz's force was unmistakable. Railway Age and Electrical World described her surging forward, delivering full torque from a standstill. The logs confirmed it: 4,600 horsepower at the rail. No electrical faults, no overheating, no slip. For a moment, Smedley's promise seemed fulfilled: a single engine taming the Alleghenies. Unmistakable. But as she climbed, another challenge emerged. The locomotive's strength rippled through every coupler and frame behind her. The test became less about horsepower and more about whether the rest of the train and the railroad itself could handle the strain Big Liz delivered. Strength. Every locomotive is only as strong as the weakest link in the train behind it. For the Pennsylvania Railroad in 1918, that link was the coupler, the Janney knuckle, forged from medium carbon steel rated by the American Association of Railroads for a maximum static tensile load of 60,000 pounds force. This figure was not just a guideline. It was the mechanical ceiling that governed every freight move across the country. Couplers connected each car, their strength setting the upper limit for how much force could safely be pulled before metal began to deform, crack, or snap outright. But the coupler was not the only constraint. Between each car, a draft gear assembly, essentially a shock absorber, cushioned the blows from starting, stopping, and sudden surges. These draft gear units, often made of spring steel or copper alloy, could manage about 30,000 pounds force. Anything above that risked crushing the assembly, permanently distorting it, or sending shockwaves down the train that could buckle frames or derail cars. These numbers, 60,000 for the coupler, 30,000 for the draft gear, were not chosen at random. They reflected decades of incremental improvement, each new freight car designed to match the power of late 19th century steam engines. By the 1910s, most trains rarely approached these limits in normal operation. A heavy consist on a steep grade might see 40,000 or 50,000 pounds force at the lead coupler during a hard pull, but the system was built with a margin for error. The engineering logic was conservative and rooted in experience. Better to have a coupler bend than a catastrophic break. Then came Big Liz. Her tractive effort of 140,000 pounds force at the rail meant that even a gentle application of power could double or even triple the force the first coupler was designed to handle. The draft gear, meant to absorb shocks, became a bottleneck, compressing beyond its elastic range. The result was a mechanical mismatch that had nothing to do with the locomotive's design. The problem was systemic. The rest of the railroad's hardware simply was not built to handle this kind of strength. Each time Big Liz pulled, the question was not whether she could do the job, but whether the train behind her would survive the attempt. The lessons of these limits would soon become painfully clear. The first test run started with a low-speed pull, Big Liz delivering her full 140,000 pounds of tractive effort. Within minutes, the dynamometer car's pin shot off the chart. The lead coupler on the first freight car fractured with a sharp report. Brakeman H.R. Cole later recalled that they heard the coupler snap like a twig. The train lurched to a halt, and the crew scrambled out to inspect the damage. The broken knuckle was tossed aside, replaced, and the test resumed. On the next ascent, the pattern repeated itself. As Big Liz crested the 2.2% grade, the force transmitted through the train exceeded anything the Janny couplers or draft gear had ever faced. Mid-train, another knuckle gave way, this time leaving a string of cars stranded on the incline. The draft gear on the last car showed signs of permanent deformation. The steel buffers compressed well past their elastic range. The hour-by-hour log recorded each failure. Lead brake at mile 7. Mid-train fracture at mile 11, draft gear crush at the summit. During the controlled descent, the test crew attempted to use the locomotive's regenerative braking system to hold the train steady. But as the train slowed, a coupler failed near the rear, sending a loaded car off the rails. The derailment triggered an emergency stop, and the crew spent the next hour reassembling the consist. The dynamometer traces from that run show jagged spikes, each one a mechanical warning that the system was overstressed. After 4 hours, the engineering team attempted a lighter run, throttling back to 80% power. This time, the train moved without incident, confirming that the earlier failures were not due to a flaw in the locomotive, but to the overwhelming force it delivered. The official memo from Chief Engineer William H. Smedley summed up the findings in a single line: "The locomotive is too powerful for our freight fleet." The verdict was unambiguous, backed by data and the broken steel scattered along the right-of-way. Big Liz had exposed the limits not of her own design, but of the railroad system she was meant to serve. Pennsylvania Railroad engineers, confronted with a locomotive that could snap its own train apart, turned first to metallurgy. The standard Janny coupler, forged from medium carbon steel and rated for 60,000 pounds force, had failed under Big Liz's pull. By mid-1918, shop crews were recasting select knuckles with higher carbon content, up to 0.65%, and subjecting them to hotter tempering cycles. The goal was to push tensile strength past the old limit, hoping a tougher knuckle could withstand the shock. Draft gear upgrades followed, with copper alloy buffers replacing spring steel, raising compressive load ratings from 30,000 to 45,000 pounds force. Yet these changes, promising in theory, only bought time. Reinforced knuckles lasted longer, but new signs of fatigue and deformation appeared elsewhere in the train. Test logs from the summer of 1918 showed fewer immediate fractures, but the underlying problem persisted. William H. Smedley's engineering team recognized that even the strongest coupler could not protect a train whose frames and draft gear belonged to an earlier era. Operational rules shifted. A July 1918 memo capped throttle at about 80% of Big Liz's rated output, roughly 112,000 pounds force at the rail. Train lengths dropped from over 30 cars to 20 cars, an attempt to keep loads within the safety envelope of the upgraded hardware. But these restrictions undermined the original vision, a single locomotive conquering the Alleghenies with a full-length freight. Seeking a solution, the railroad authorized helper locomotive trials. On October 15, 1918, Big Liz led a consist up a 2.2% grade, with a steam pusher at the rear. Strain gauge readings from the dynamometer car recorded a sustained 95,000 pounds force on the lead coupler. The reinforced knuckle survived, and the train completed its climb without incident, a rare success. But the helper strategy demanded precise coordination and extra crew, erasing the hoped-for efficiency. Each fix chipped away at the problem but never solved it. By late 1918, field reports made it clear the real barrier was systemic. The railroad faced a machine that had outgrown its own era, and quick fixes would never be enough. Today, technology still outpaces infrastructure. From electric grids to digital highways, Big Liz proves that breakthrough ideas can fail, not from their own limits, but from the system's inability to keep up. Progress demands more than invention. It requires readiness. Sometimes the future arrives before we're prepared to use it.